Hello everyone. Let us discuss a problem from classical mechanics. The question is, a particle of mass m kept in a potential v of x equal to minus half kx square plus 1 by 4 lambda x raised to 4, where lambda comma k are positive constants. Undergoes small oscillations about an equilibrium point. The frequency of oscillation is four options are given. Option A, 1 by 2 pi root 2 lambda by m. Option B, 1 by 2 pi root k by m. Option C, 1 by 2 pi root 2k by m. And option D, 1 by 2 pi root lambda by m. We have to find out the frequency of oscillation. It is given that the potential V of x is equal to minus half kx square plus 1 by 4 lambda x raised to 4. The particle of mass m, which is kept in this potential, undergoes small oscillation about an equilibrium point. Potential is given. The particle of mass m undergoes small oscillation about an equilibrium point. Now suppose this equilibrium point be some x naught. We can denote this equilibrium point be x naught. Now for a particle of mass m to undergo such oscillations about an equilibrium point x naught, then that equilibrium point x naught must be a stable equilibrium point. This equilibrium point x naught must be a stable equilibrium point. Then only the oscillations are possible about that equilibrium point. For convenience, let us denote this point as x naught. So what is stable and what is unstable equilibrium point? We can classify equilibrium as stable and unstable equilibriums. Now at equilibrium, the first derivative of the potential is 0. That is, at equilibrium dV by dx is equal to 0. Now the equilibrium can be stable, the equilibrium can be unstable. So what is stable equilibrium and what is unstable equilibrium? If the equilibrium is stable, then the potential is minimum at that equilibrium point. That is, for stable equilibrium, V of x is minimum. Then we can represent it mathematically as the second derivative of the potential, that is greater than 0. Whereas unstable equilibrium means V of x is maximum or d square V by dx square less than 0. Now the oscillations are possible if the equilibrium point is a stable equilibrium point. Now the condition for equilibrium. that is dv by dx equal to 0 firstly. Now let us write the given potential v of x, that is equal to minus half kx square plus 1 by 4 lambda x raised to 4. Now what is dv by dx? dv by dx is equal to minus kx plus lambda x cube, minus kx plus lambda x cube. Now we can write it as, and this is 0 because at equilibrium this is 0. We can write it as x into minus k plus lambda x square is equal to 0. So we have two solutions, two values of x which satisfies this equation. That is, when x equal to 0, dv by dx is 0, and also when x is equal to root k by lambda, this equation also 0. So we have two values for x. One is x equal to 0 and another is x is equal to root of k by lambda. These 2 points are equilibrium points. Now what kind of equilibrium it is? For that we need to check the second derivative of the potential. If it is greater than 0, that is a stable equilibrium, and if it is less than 0, which is an unstable equilibrium. Let us check d square v by dx square at x is equal to 0. What is d square v by dx square? That is minus k plus 3 lambda x square. Now at x is equal to 0, we can say this d square v by dx square is minus k. At x is equal to 0, our d square v by dx square is minus k. Now in the question it is given that k is a positive constant. So we can conclude that d square v by dx square is less than 0. At x equal to 0 is less than 0, which means x is equal to 0 corresponds to an unstable equilibrium point. X is equal to 0 is an unstable equilibrium point. Now let us check the second derivative of the potential at x is equal to root of k by lambda, which is also a solution for our equation. Now d square v by dx square, that we already know, that is equal to minus k plus 3 lambda x square. Now at x is equal to root of k by lambda, our d square v by dx square becomes minus k plus 3 lambda k by lambda, that is 2k. Since k is a positive value, we can say that this second derivative d square v by dx square, which is greater than 0, when it is greater than 0, this x is equal to root of k by lambda is a stable equilibrium point. So the mass, so we can say that the object is oscillating or undergoing small oscillations about x naught is equal to root of k by lambda. Our particle of mass m is undergoing small oscillation about this stable equilibrium point x naught is equal to root of k by lambda. Now we have to find out what is the frequency of oscillation. It is asked in the question, we have to find out the equation of we have to find out the value of frequency of oscillation. So what is the equation for frequency of oscillation? Here we use the relation omega is equal to square root of d square v by dx square at x is equal to x naught. What is x naught? X naught is the stable equilibrium point divided by m. Omega is equal to root of d square v by dx square at x is equal to the stable equilibrium point divided by m. This is the equation to calculate the frequency of oscillation. Now we have d square v by dx square at x is equal to x naught, which is nothing but 2k. So we can say omega is equal to square root of 2k by m. Square root of 2k by m. Now we know that omega is equal to 2 pi f. Therefore, the frequency f is nothing but 1 by 2 pi root of 2k by m. F is equal to 1 by 2 pi root of 2k by